Hello and welcome to another exciting video from Hyperactive Studios. My name is Nate Nestler again, as always, and we're going to be continue on with some of the 3D graphic programming transformations here as we move into programming with shader languages and the overall 3D graphics programming. Alright, so here we have, I did make a mistake here as modeling space here when it should have been modeling transform. So basically we want to have object space being multiplied times the world space, transform matrix, which will give you the position of that model in the world space with positioning the vertices. And we went over all that in the last video about how we're going to actually go through and model each vertex, over here in this model with the polygons and moving the vertices points around. Oh, and by the way, a n-gon would be a 5-sided or more polygon. Forgot to mention that in the last video. But that's what an n-gon is. And it's bad for everything except for physics. It's really bad for graphics. It's great for physics. We've got a totally different requirement versus visual versus physics calculations. And just to get into the amount of calculations required in order to do a physics collision is the reason why that's the case. But here we are with our basic setup here. Now, real quick, moving from world space like we saw, we get into our eye or view space as it's called. Now, important thing to note about the eye or view space is it's literally at the center. This is kind of weird, but when you get into OpenGL and such, there's no and probably DirectX too. There's no camera necessarily as part of the language. Instead, everything is viewed from the perspective of your center point. So quite literally, you don't move the camera, but you move the entire world and all the objects in it. So say you want to move the camera forward like 5 units, you literally take the entire world and move it 5 units forward. And it looks like the camera is moving through the world, when in fact the world is moving through the camera. So it sounds, you get the same effect. It gets the exact same look and everything. But just realize there's no camera inside this setup, inside the system. We have an arbitrary camera, and there's a way of setting it up to where it acts like a camera, and this is, well, way above and beyond this particular video. We'll get to it later on. It gets into something called scene graph, where you can then lay out and have it positioned and such for handling the objects in here. But that's way above and beyond the scope of this video for now. But there is a way, that's why you see this little CG camera over here. Like I said, it requires scene graph to make that happen, and that's above and beyond this topic here. But essentially, we have our scene right here, and we would be at 0, 0, 0 for the camera, and it would be shooting straight down here, and this would be Z, typically down the Z axis. Now in this case, Blender it's Y, but in our examples and in our methods for our programming, it's going to be Z axis straight down the center here. And this would have this setup. And say I wanted to have this model viewable in the camera. What it would literally do is move this model out like that, and then from my perspective here, it would look like I'd move the camera back 5 units or whatever, when in fact that isn't the case. And of course you can see why. Again, you would have to move the camera back, otherwise you're inside the model. And this would actually literally stop light from coming in. If we had light set up, so that'd be a problem too, because light's going to strike the outside surface of this model. And there's a vector called a normal. It's coming off the surface at a 90-degree angle here in this faceted method. We'll get into some other methods for doing multiple normals across the surface through bitangent, binormal calculations here. But anyways, basically just smoothing operation that's what it does when you do that, what I was just talking about. But basically in this mode we have a 90-degree angle here from the face for this vector coming off, and it's called a normal. And depending on which direction that normal is facing, it depends on whether or not the light hitting the surface makes that face visible, the polygon visible. Face, polygon, same thing. more or less. You can refer to it. Now you can have a polygon model here, but be made up of many faces. So that's where it gets a little confusing. We're talking about a single polygon, you're talking about a single face. You're just talking about a face, so it gets a little confusing there, but that's what they're talking about. Oh, and there's also edges and lines. So you see right here, if I switch over to edge mode real quick, you see that line. That is an edge, and that's a segment of a polygon, sometimes referred to as a segment too, yes. Many different names for this stuff, and then again, a single polygon selected as such. Okay. But in the way we view this model, we're talking about view space, and that's basically what we're talking about here. Is the from that center point. Now, going further, let's switch over here to our diagram, and we have a view transform here. So this lets us transform the view. And orthographic or projection transform with our clip space. Now orthographic, we don't really do any distortion, so you don't really do anything. But when you're talking about perspective distortion, you are distorting it. And let me just point this out. You notice how this part of the model here is suddenly bigger on this part of the eye versus this eye here. And that's because this eye is closer to the camera, when in fact that is not the case. Now if I were to view this from an orthographic view, even at a perspective angle, check it out, the eyes are exact same size. And that would be the reason for orthographic views. Now for a lot of games, you're going to be using perspective view, but also orthographic view, both at the same time. I'll tell you why. Most time for the game, if you're doing first-person shooter, or even third-person, it doesn't matter, that camera which you're seeing the whole 3D scene is going to be a perspective view. Now the view in which you're using to see the actual interface for the game, like the HUD, heads-up display, your buttons, your layout, what are you going to click on to interact with the game, maybe life bar, what items are in your inventory, all the stuff. That's done with the orthographic view. Why would you want to do the actual heads-up display HUD, or your what you would call it, a layout, for your units, for your buttons and such things of this nature, for your interface layout? The reason why you're going to want that to be orthographic is because you want the button to be the same size towards the center of the screen as it is towards the edge. You wouldn't want the buttons to literally warp as it got towards the center of the screen versus out towards the edges. Of course, that would look incredibly stupid. So what you want, of course, is for that to be a nice, even, smooth, no distortion on that. You just want it to be a button, So you're going to want it to be orthographic, so that way it's just going to be nice and smooth and even everywhere. Now in the case of when you're looking at through the game perspective view like this, you're going to want projection. So you're going to want a perspective distortion view. And this gets into simulating like a real camera. So say we have a 45-degree f45 lens, right? Focal length of the lens is 45. Well, cool, that's fine. And we can simulate that in the computer. And that's essentially what we're doing here. Check it out. I'll show you what I mean. Okay, so say I go and I look through this camera instead here. Okay, so I'm looking through this camera, great. And I have my camera selected. And I want to start changing properties of this camera, for instance. So right here I have my focal length of the view. So you can definitely see the focal length is changing how this is being viewed. Check out this whole grid. It's really changed. I've gone down to a focal length of 6. This can make it look like a hall is so much longer than what it is. You can literally mess with people. Say they're going through some kind of weird trippy dream or something like that in the game. All you have to do in order to give that effect would be to simply just change the focal length of the camera. Make this where the artist can sit there and manipulate it easily, and then they can sit there and make it look like the hall is stretching, elongating as they run, or weird stuff like that, moving back and forth on the focal length as they move through the level or something of that nature. You could create that and you could cause that to happen. Looks like we're zooming, but we're really not zooming. We're actually changing the focal length of the camera. Now you can't do this in real life. You can't actually take a 50-degree focal length lens and suddenly just start morphing and changing the shape of the lens on the fly like that. It's impossible. But in CG you can. in computer graphics. That's what CG stands for. So there's all this great stuff. You also know something else here too, and that gets into so you get into your view space here, but we also got clip space. Now clip space, and let's have a look at this real quick. You got your orthographic projection transform, so we're going to multiply our eye space, times the matrix in here for going for the eye space to clip space. And what does a clip space involve? Well, this really just defines, is it in frame of the camera? Are we going to be interested in things outside of the camera? Answer is no, of course. You don't want to sit there, say we have a huge massive scene, there's all these things running around off camera. Do you really want to see what's off camera? Of course not. It doesn't matter. If it's off the camera, you don't need to see, you don't see it. What's the point of calculating that? So here we're going to take a look at clip space. So this is what's referred to as clip space, where we determine is it within frame of the camera. And we have also called sometimes clip position, clip coordinates, things of this nature, where you get the position back for doing your 3D shading with clip position. In this case right here we got our clip planes. Alright, so it's impossible to sit there and calculate out to infinity. It'd be great and everything, but think about it. Theoretically, the scene would go on forever, into infinity and beyond. Of course, it's impossible, but whatever. The calculation would go on into the depth of nothingness forever, and way beyond the length of your level and your space. So, in order to make it manageable for how far out a character can see, or something like this, or compute before we start loading in models and things of this nature, we have clip planes. Then we have far clip plane and close clip plane, or near clip plane. So here's the near clip plane for the start. Now I can prove this, that this is indeed the case. And notice that the model literally starts to disintegrate, it looks like. That's because my near clip plane is saying that we don't need to render this stuff. Render means take the 3D model and convert it into a 2D image to be displayed on the screen. That's what rendered means. It's used from an art term when they're talking about drawing, sometimes referred to as rendering or painting or whatever. Basically means create an image, more or less. And here you can see I'm changing that on the fly here interactively. Now you can set this up in your programming too, and this is also available to you in OpenGL or DirectX. And then we have our ending clip plane. Now I can increase this to add for more and more space, or I can decrease this. I'm going to decrease it just a good bit here. Here it comes. And here's our far clip plane. So now technically, do I really need a far clip plane above and beyond this model here? If I'm just rendering this model and it's against nothing more than like black or something of that nature, really right about there covers me, and then really about right here or so covers me. And I really don't need anything outside of that, and thereby diminishing our domain of which we have to render stuff at. It speeds up our calculations for our rendering and our computing. Because basically we're not having to compute empty space that doesn't need to be computed. So this can always add for a performance gain. And that's the whole reason for this, by the way, is for performance reasons. And so that's your clip planes too. And we talked about clip space and clip planes and clipping positions and our clip coordinates. Within this view would be clip coordinates. So there's your clip space, and that explains how that is basically set up. So again, that has its own matrix for defining its space. Now you'll notice something here. We have this camera center point here, and just try to hit this home a bit. I'm going to change this to a normal. I'm not going to explain that right now. I'm just going to break off another camera real quick. I'm sorry, I'm not going to explain what I'm doing here. But essentially, if you think of it this way, let me go ahead and scale this up. So alright. So say our camera here is like this. And I want to encompass this monkey head. You can see here we have our center point of our camera. This is our point which our camera starts to see. And then out here is our far space here. Now, and this gets into what's called the view frustum. And the frustum is literally quite just like this. You're not going to render things outside the view frustum, because if you do, what would be the point? Only the camera sees what is within this space here. So thereby only rendering what is in this space. Of course, it's smart to do this. Now, if I had the monkey here and I moved it out part of here, then only the faces that are within this camera's actual space here of this frustum, this view frustum, is going to get rendered, and everything else outside of that is not. So, we can do a determination. It's called view frustum culling. We're not going to get into that, say, optimization method. There's some other ones too out there that's called KD trees. And there's other methods. KD trees is particularly fast. It's extremely efficient. There's, well, they've shown where people can get anywhere from about 35 times to 3,500 times faster computations by using KD trees for the game. That's quite significant. You can mix that with view frustum culling in order to speed up even further, which is awesome. But here we have this object within the frustum of this camera, and so now we can see it. There's a method for doing this mathematically using the dot product in order to find whether or not a model is within this frustum. Basically, if it's outside this angle of view, and this gets into your angle here of your camera, of course. We're messing with the F angle there. That's going to change the width of this camera here across the space and widening out the range at which it's viewable for the camera. Very cool. And that's what that calculation does from a visual standpoint of that space, shape, and form of the camera. Alright, so that's very cool, but what about some other things here? Now, with the dot product, if we have we can create something called a facing ratio. Is the polygon within the actual angle of the camera or not? If the polygon is facing away from the camera, we don't need to render it. Obviously, if it's on the back side of this model, I mean seriously, are we really concerned with the polygons that are on the back side of this model? And the answer, of course, is no. We're not going to see them, right? Because if we're looking at the camera from here, I can't see the polygons on the back side of this, monkey head. So therefore, we don't need to calculate them. We don't want to render them. And so, that gets into our facing ratio for our calculations with our dot product. And again, that's a reason why math series is so important and why all these formulas are so such a big requirement, and why it's so desired in order to go through this material. Okay, so with that said, let's have a look at what we've got going on here. Okay. Alrighty, and that covers the whole view frustum setup, and that gets into our projection matrix, of course. So this is our projection transform, because we are going to have to distort. Okay, let me explain that a little better. I should mention this. Okay, so say I'm here, and you see this model here, and its distortion of this model is completely based on, let me break off a separate view because it's just easier if I do. Alright. Okay, so I'm just going to zoom this in real quick like this and manipulate this camera as it moves through the scene here. You'll notice that we are getting more distortion here on polygons. They're closer to the camera. So, of course, we have to multiply that matrix by our projection matrix here for our perspective distortion. So that way the vertices that are closer to the camera are literally distorted. They are moved, they are scaled, they are warped, if you will, to where they are bigger when they're closer to the camera and shrunk in as they move away from the camera. And this causes us to simulate real-world lens distortion. Humans have about a 48.5 lens distortion with their eyes. People, a lot of times, for photographers, will simulate this with a 50mm lens because it will pretty much let you get pretty close to that accuracy on it. So you'll see in a lot of CG they'll go 45. It gives you a fairly good approximate also of the human eye. But if you want to get a little closer to it, you can do about a 48.5. It doesn't really matter. No one's going to really be able to tell the difference when you're talking about that much of a minute change there. It gets really hard to tell. But and 45 is a nice even number, I guess. well, odd number technically. But here we have our polygons that are moving towards, and then you get that perspective distortion, and you're going to multiply times that matrix there. So and this gets into what's called the model view matrix. And some of you may have heard this before if you looked at any 3D before, and you hear about the model view matrix, but no one ever explains it. This is literally the model view matrix, this pipeline of how the 3D graphics programming language literally handles it on the 3D card for each part. Now you don't have to do much of this. This is the great, wonderful part. You're like, well, why are you telling me about all this stuff if I don't have to do much of it? Because you have to understand what it is that's happening so that you know how to manipulate it in your program and know how to change and edit things on the fly in order to make it do what you want. Because if you don't have a good understanding of this, you won't be able to do that. So that's a very important aspect here. Okay, so that's really important part to understand here, is that these coordinates are going to be multiplied through these matrices, and it creates what's called the model view matrix. We're almost done with the whole process here in the chain. If we go have a look at this, we've already talked about clip space. Our perspective division. What is perspective division? Well, perspective division gets into your well, more or less your homogeneous form of your normalized device coordinates. What do we mean by normalized? Well, if you normalize a vector or whatever, you make it go from 0 to 1, and you get rid of the magnitude of that vector. So now you're only talking about the actual direction and not the magnitude, position and direction of the vector, and not the actual magnitude of the vector. So it takes away the actual force, if you will, from that vector for the most part. So that lets us get a 2D position, an X and Y pair, along with the depth value, of course, which you get into depth buffering for rendering visible surfaces, and that gets into doing things like transparencies and things of this nature and the order in which they're rendered. I'll get into that in just a moment. Perspective division, on the other hand, or perspective division, as you can see it here, that gets into your normalized device coordinates, or basically dividing x, y, and z by w. So that's basically sets you up with perspective division, and that's why it's called perspective division, because you're dividing it by those coordinates in order to get the perspective distortion. Okay. Alrighty, so we've seen what the view frustum is, and we've seen clip coordinates, and we've seen perspective division now, and normalized device space has been explained too. Let's talk about your view depth transform mathematics operation. These are all different matrices here that we're multiplying through for each part, and then we get into window space, which is literally the final actual image that displays on your monitor. Okay, and that's the final part of this whole process. Okay, let's talk about view port depth transformation. So basically what that means is, okay, so a good way to explain this is, let me come in here and let's just add, oh, I don't care what it is, a torus. Something a little more interesting than, Okay, so say this torus right here, which is nicely in the way, but I'm going to go ahead and just smooth those normals. Okay, I'm going to add a material to it real quick, and transparency, Z transparent, and it's not really showing up right now. That's okay, we can change that real quick, because I'm just going to turn on GLSL shading instead of multi-texture. Alright, and change this around to texture solid shading. Okay, and so here we are, we're seeing some transparency happening here on this model, and I can bring this up. Now obviously this is being drawn correctly, so to speak. I could get rid of the I could get rid of the whole, so we go back to flat. It doesn't matter, it's still gonna be the same ugliness. Okay, well, it doesn't matter. It gets the point across. Okay, so obviously I can see this monkey behind the through this torus, right? And that gets into depth order. And so this is the reason why the depth part is so important, because the order in which I draw this on the screen matters. Say I were to draw the monkey before I was to draw this torus that's closer to the screen, and this torus is a transparent object. That means the monkey is going to appear before in front of the torus object here, even though the torus is in front of it. So needless to say, if you screw up depth order for drawing, you're going to get some really whacked out weird graphics occurring on the screen, and that's going to look terrible. So what you have to do in order to prevent that is quite simply have the depth order correctly drawn. So we can create this as a depth image or depth pass, right? And then based on that, we can determine which object is drawn in what order and on the screen. So we're going to draw this monkey first, and then we're going to draw the torus over it, on top of it, if you will. And so that order matters, and it's based off the depth channel there. And that's what we're talking about when we're talking about this depth transformation. So, you have to, and moving things back, of course, and all this stuff. And that matters. That's important. So, for a lot of things, actually, quite a bit of number of things it's important for. And again, in Windows Space, it's just your finalized image that you get on your screen. Like we're getting this image right now on the screen. This is what we see on the screen when this is all said and done. You end up with this image here on the screen. It's nice and ugly. But when we start doing some other stuff here with the 3D graphics, you'll see a lot of very cool effects where we can do everything from like fire to, oh my gosh, you can do all kinds of stuff now. We got real-time cloth going on in the games now, and you're talking about real-time fluids happening. It's insane. It's really awesome. They're actually starting to implement film techniques now in the games, stuff you guys haven't seen before if you haven't been in the actual game industry. They're getting to the point where games look like movies because they're actually implementing film techniques in-game right now. Now, you're not going to see these games for the next, I don't know, 3 to 6 years probably, but regardless, because the frame rate's terrible on them, but they're pushing like 600 million polys in a single game level at once, and the frame rate's terrible right now, but it won't be later on here. And so the next generation of games that's going to be coming out are just going to look absolutely insanely awesome, and we'll be going over some of these more advanced techniques and some of these other new advanced languages that just recently come out. I do mean quite recently, and how we can work with those. And also from a realistic standpoint of let's not reinvent the wheel from scratch, and how can we get things done in a time conclusive manner. You don't want to sit there and develop something from scratch for every little thing that takes forever when other people have already done it and it's already been released and you can make use of it with no problem. It doesn't make sense to reinvent all that stuff all over again. So we'll have a look at it, but yeah, we'll still go over all the techniques and what's involved with each one so you can understand each part as we move along here. Alright, so this is how the view system works for coordinate system within CGFX inside of a real-time environment. And so this is literally what's happening inside OpenGL, DirectX, etc. And this matters for our series here on real-time programming. And we'll keep calling back over to this over and over again. And then now when we talk about the ModelViewMatrix, now you understand what we're talking about. We're talking about this whole process of where we're multiplying these different matrices out across each step here through each part of this, operation pipeline here in order to get the end result of the actual position for this vertex or point in space to be transformed or manipulated in the shader. And so we'll get into that next, where we'll start moving into shader programming. And if you haven't looked at the mathematics videos, it'd be a good idea to definitely check those out, because moving forward here we're going to be starting to hit some of the higher up mathematics, and you do need to have a good basis before you can move forward. It's important to note that we're going to be working with some shader programming applications in order to make life easier, to help you hunt down errors faster and easier, in order to get better visual feedback, and just to help reduce the complexity. Most programs and most videos and books throw you right into the thick of things. We're going to be avoiding the fixed function pipeline now. The fixed function pipeline
is the old way of doing things, and it's pretty much been ditched by the industry. Like when OpenGL from the Cronus Group asked, because they're now taking over the Cronus Group from SGI, asked, out to the industry, and it's like, okay, so this fixed function pipeline, do we need to support it anymore? And they got back and no, pretty much. The reason why is because it's the new shader system. The way you do it now, you can actually tell it to do whatever you want for shading, for the most part, within the limitations of the hardware. Previously, you couldn't do that. You had to work with a single shader model that's been like a little bit enhanced or whatever, but you're pretty much fixed to that. And that's why everything looks like plastic pretty much in the earlier games. It's because that was the only shading model they had to work with, plastic, pretty much. Now you can really change the look of it to where it doesn't have to look like plastic. You can make it look like, well, all kinds of different surfaces, metal, whatever, and literally have it look like metal or carpet, or it's, not much of a light influence on that surface or whatever. And so we can get a lot more realistic, a lot more accurate shading capabilities. We also, some of the new shading methods out there, we can also actually do geometry shaders, which is crazy. You can actually create geometry in a shader. On top of that, they have a new one for doing a tessellation shader, as it's called. This lets you add polygons on the fly. And so you can basically say, well, if it's closer to the camera, add a lot of polygons to make it super detailed. Now, this is what reason why people are able to push 600 million polys in these games, because they're sitting there creating these super detailed models when they're up close to the camera, and then they reduce the poly count as it gets away from the camera. Who cares? If it's way off in the distance, you can't see it's not very detailed. You know what I mean? Doesn't matter. Well, who cares? Why does it matter? But if it's up close, it matters if that model looks detailed or not. So here we can actually do it in a very efficient method of increasing the poly count to the point where it's like film, as far as the details of those models go, up close, and then as it goes off into the distance, it's, nothing big at all. It's like super small as far as the poly count goes. Absolutely amazing. So those are some of the new techniques that just recently been released. We're going to start with the ones that are more supported by more 3D cards. Some of the tessellation shader stuff, I've been hearing NVIDIA 500 series, we had to have one of the new 500 cards in order to support the tessellation shaders. I've done it on a 400 series card and a 200 series card too, so I don't know about that. It's supposed to be OpenGL 4.1 supported only for the 500 series and 3.3 for your 200 series and your 400 series cards. But I've been managing to make available some of those features. For this reason, you may really want to consider getting a top-of-the-line game card. Now, I'll say game card in particular because game cards are set up to render a single view and not multiple views. That's what the Quadro cards are set up for the 3D graphics. And those cards are about $1,000 to $2,000 typically, sometimes $3,000 for one. And that's what I had to buy when I was going to school. But because I was doing the film graphics stuff, and these 3D applications for the film graphics prefer the DCC or the basically these Quadro cards. They're set up for doing the multiple viewports simultaneously and a lot of other cool features on them. Unless you're doing that type of programming, you don't need one of those. Quite frankly, you're just as fine with one of the game cards. You can sit there and spend only $500 or $250 and get a decent game card that will let you do this programming. Note, you will need a decent programming card to do this stuff. If you have Intel integrated, you are out of luck. I hate to say it, but that is a terrible ripoff. The Intel integrated series doesn't support anything beyond OpenGL 1.0, pretty much. It's the fixed function pipeline. It doesn't support programmable shaders. It's just about useless. I don't even have words for it. You can't hardly get anything to work on it. It doesn't, you have to go back so far on it, it's ridiculous. They've put it in so many computers that, because it's cheap, basically, is the thing. It's just cheap piece of junk for the most part. And if you want real graphics processing, you need an NVIDIA or an ATI card or something like that. Those are the two main companies. I will recommend towards an NVIDIA card for development. And my reasoning for doing this is when we get into doing cross-platform programming, so we want to work on Linux, Windows, Mac OS X, etc., you're going to want an NVIDIA card because ATI doesn't write drivers that hardly work at all on Linux. Really, honestly, it's NVIDIA or nothing when you get to Linux because you're going to be going with open source drivers and they suck. You definitely want the proprietary drivers from NVIDIA on Linux, and it makes a massive difference for your capabilities on there. So if you're looking at getting a graphics card and you realize you don't have what you need, and you need to check your system if you don't know, you can go to Windows to the control panel and check it out there and find out if you have an Intel integrated card or if you have an actual real 3D card. And it's fine if you have an NVIDIA integrated or ATI integrated card, then it will work. And there's some benefits to that, actually, believe it or not, because having that on the actual motherboard with the CPU means you can do shared memory between the GPU and the CPU that's on the same board there on the motherboard. It makes it faster for interactions versus going over the SLI bus. But anyways, I'm getting ahead of myself here. It's getting some more detailed than we need to. But there's definitely some capabilities by doing that. You're still, I would say, better off having some of these. I would recommend a 200 series card or higher for a lot of this development, so that you can make access to some of these newer features, and especially when you get into like OpenCL or CUDA, having access to these multi-threaded cards. Now, technically, yes, you can do the coding in the older cards too for CUDA and OpenCL, but you will be missing some of the features. And in addition to some of the shading layers, there's been an explosion of what's going on. And if you want to be up on the latest techniques and everything like that, then you definitely need one of these newer cards, and there's no way around it. But with that said, let's move on to the next part here, where we start doing some shader programming. Thank you very much. Again, my name is Nate Nestler, and this is for Hyperactive Studios. Thank you very much.